Hey everybody, just coming back to our distance learning for Unit 1, Newton's laws, circular motion and momentum. I talked about in the last video how it seems like it's new material, but it's really just based off of things that we've already been working with all year long. So now we'll take a look at a problem that, again, involves something new, the impulse momentum theorem, but it's really not new. So what's old becomes new again, and here we go. So a 1,300 kilogram car collides with a tree while traveling 30 miles per hour. The collision occurs over a time of 0.05 seconds. Determine the magnitude of the force exerted on the car as it comes to rest during the collision. And it's easy enough to just do a quick Google search. 1 meter per second is about 2.24 miles per hour. So we can convert between the English system of miles per hour to a velocity that we'd want to use in the science world with the metric system. Okay, so here we go. So just to kind of have a little visual to help us process all this. Not allowed to make fun of my car, just like when we're in class. So we know here that the car is going 30 miles per hour, and then ultimately it's going to stop. So the initial velocity is 30 miles an hour. The final velocity is going to be 0. So obviously we have to have some type of force to decelerate this car. So that brings in Newton's second law of motion, F equals ma. Well, here's where we're going to take something that's old and make it new again. So we know that acceleration is really just defined as the rate of change of velocity, delta v over delta t. So we can do that substitution right here. So we can rewrite Newton's second law as F equals m delta v over delta t. Now, if we multiply both sides of the equation by delta t, that's going to give us what's referred to as the impulse momentum theorem. F delta t equals m delta v. So on its surface, it looks like it's new all by itself, but it's really just combining forces and motion concepts we've already talked about. So this is the impulse momentum theorem. Where the F delta t, that product, that's the impulse. And if you think about what this is really telling us, if you apply a force for some block of time to an object, it'll change the velocity of that object or of that mass. So that's really what this is here. So now let's take that to figure out ultimately what force is exerted on the car. So with F delta t equals m delta v, the impulse momentum theorem, our unknown is force. We're looking for that force, and we know the time, we know the mass of the car, and delta v, the change in velocity, well, if it went from 30 miles an hour to 0 miles an hour, we can work with that. So we'll do a little dimensional analysis here for our velocity. So 30 miles per hour. Again, a quick Google search will tell you that 1 meter per second is equivalent to about 2.24 miles per hour. So we end up with, this car had an initial velocity of about 13.39 meters per second. And delta v, the change in velocity, take the final velocity minus the initial velocity. So we're really talking about 0 minus 13.39 meters per second. So delta v is, our change in velocity is about negative 13.39 meters per second, because that's how much it slowed down by. So now coming back into our impulse momentum equation, our unknown force, which is applied for 0.05 seconds, that force applied for that amount of time will make this mass change its velocity. It'll make a 1,300 kilogram object, in this case, decelerate and slow down 13.39 meters per second. So what we end up with here is 0.05 times the unknown force that we're looking for is approximately equal to 17,410.7 negative. Now from there, divide both sides by 0.05. So we end up with the force acting on this car is about negative 348,000 214 newtons. Remember, force is a vector quantity, so the negative sign just shows direction. It's a force working against the motion of the car. So to tie it back to impulse momentum theorem, if you apply a force of about 348,000 newtons for 0.05 seconds, it'll make this 1,300 kilogram car slow down by about 13.39 meters per second. So for all of you that make fun of me for wearing my cargo shorts like it's 1995, just like we saw with these equations, the old stuff comes back and it becomes new stuff. So I'll be laughing soon when cargo shorts come back around. Raider Nation.